Hello everyone, welcome back to the channel. My name is Matt Kosvek, CEO and co-founder of DataForge. And at DataForge, we look to automate the tedious and simplify the complex, specifically for data engineers and helping them build data platforms in a way that is simple and scalable and easy to operate. In our last video, we took an overview of an existing complex data platform built with a combination of Warescape on top of Oracle that had a large number, over 4,000 scripts to support the platform. And we went through that full example and discussed how there's a great process to building a solution from scratch, leveraging existing scripts within DataForge. Today, in this video, we're going to take a deeper dive into how to do that. This is going to be a little bit less formal. We're going to move quickly through an example. This one's a relatively complex example, just to highlight how to think through these types of complex transformations and how they map from a complex set of stages, a large number of scripts, to the DataForge framework, and how that transition ultimately simplifies the overall solution and makes it more manageable overall. All right, so let's jump in. We are recording. Okay, so let's start with the end in mind. So in our example here, we had this existing solution where we had application tables, the load, the stage, the hub, a whole bunch of complex stuff, and then these facts and dimensions. Today we're going to look at populating the primary fact of this Kimball model. And then we're going to leverage all the scripts to build the solution in DataForge. So again, through my analysis, through just some basic business understanding, I learned that the target fact table was called fact OMR bound. So I guess first things first, where are we searching? I was given by the client a Git repository with all 4,948 scripts, which both do the DDL and DML. So a combination of create statements and update statements to run the pipelines. Now there's a separate orchestrator that runs on top of these scripts to run them all in the correct order. That's handled by Warescape in this case. But this raw code has all the logic we need in order to rebuild the exact same transformations in a different tool. So as mentioned, I'm going to start with the end in mind. Let's work from the target and back towards the sources where the data comes from. And what we're going to do is go column by column. So again, with DataForge, rather than thinking about stages and having to think about the entire solution all as a holistic platform, utilizing our framework, you can think about each column independently of each other, and that becomes a very powerful approach to, again, accelerate and simplify the development and then, of course, long-term operations. So let's take a look at fact OMR bound. And so you can see by searching here, we have a mixture of make statements and update. You can see we have the primary fact, and then we have a couple month to date, year to date. Today we're just going to focus on the normal fact table, not the aggregated ones. And so the process is going to be start with the end table, start with the final destination based off of the lineage of this, and we're going to trace our way backwards. We're going to open up this update statement. We're going to see what columns, or what for this specific column that we're going to be analyzing, what tables populate, or what stages previous to this script populate that column, and continue to work backwards until we hit the raw data. And then from there, we'll be able to understand all the calculations and transformations required to ensure and replicate them appropriately in DataForge. So with that, let's pop open this update statement. So here, this is again an Oracle stored procedure generated by Warescape. There's a whole bunch of detail here, but if we look, there's actually no logic here. It's just basically taking a intermediary table and doing a quick filter on it and then copying it to the final fact table here. So if we kind of parse this out, which again, you maybe need some Oracle expertise, but it's not super difficult if you know basic SQL, you'll see that actually all the columns for this stored procedure are coming from this IM stage F bound, right? So we could then go and search for that, but I have it already open here. If we jump over to the script that is update IM stage F bound, this is where the data for the fact table is coming from. We can then take a quick peek here and see, hey, there's a couple transformations here. But now that we're in somewhere where there's some transformations, some things happening, let's zero in on one specific column. Let's do the analysis to understand where this column expired premium comes from. So for expired premium, we're now going to trace back the lineage, column level lineage, manually through these scripts to understand what the transformations are that populate this final target column, where the data comes from, and then how we'd replicate that logic within DataForge. It's usually going to be a one-to-one, but we'll talk through the details for this example. So now focusing in on expired premium, we can take a look at where is that coming from. It's coming from this S policy term. So if we come down here, there's some joins. It's always important, right, to make sure if it's a left join, you're thinking about the granularity of data. But in this case, it's a straight join, so we know that this S policy term will be at the same grain as what we care about. So now we're going to take a peek at where does S policy term come from. So you can see there's really no transformations. We're not at the raw data yet. We have to continue to work our way backwards. So we then go to S policy term. And again, you can see how this process goes, right? And we then work through this one and say, okay, is there any logic happening here for the expired premium field? And according to this script, there is no logic. It's a straight pass-through column. We don't really need to analyze why this is built this way. We can just focus on the logic. So continuing to work our way backwards, we go to BV stage load from S policy term. And we now do have quite a bit of logic built into this script. And now let's take a look at expired premium, and you can see we do have some logic here now. So now that we've kind of taken a couple jumps, let's start diagramming this out, because if you look at this case statement, you can see we actually have data coming from a couple different tables and multiple fields that are being leveraged in order to calculate this logical new construct in the business logic called expired premium. Here we are, it's the next day. Thankfully, it didn't take me a whole day to build this. Just had to work on a few other things in the meantime. But we have the full lineage from all the columns that feed into this final target of expired premium, built back to the tables they came from, the original source system, as well as all of the queries or transformations that were built in the legacy system to do the logic, the business logic in the legacy system. So leaving off, we were at expired premium. Here we saw that expired premium through some case statements was combined from these four tables. One of these was pretty complex. This non-renewal indicator was then combined from these 7 tables, so on and so forth. We're going to dig into the logic here as we build it back up using DataForge. But the high level is the large amount of the logic here. The primary complexity is about detecting for a specific account what was the previous policy for that account. So this is an insurance data set where policies are renewed, typically on an annual basis, but not necessarily. And there's a metric around this non-renewal indicator and this expired premium around checking the previous policy, seeing some metrics about that previous policy and comparing it to the new policy, and doing those calculations as part of the pipeline to generate these new metrics, which are then easier to report on within the data warehouse. What's interesting is you can see here there's a lot of lines. This is where most of the logic kind of sits, is at that layer to convert to existing basic data to this previous policy logic. And funny enough, when we are going to dig into it later, you'll see that actually by adding a stage here, by adding an intermediary logic, they could have actually simplified a lot of this complexity. However, despite creating stages at many other layers where it was, call it, less needed, they decided not to create one here. So again, we'll look at that and how within DataForge there are no stages. You just build rules. as we dig in. But again, just kind of taking this all the way to the original source tables is when digging in here, you can see there's 1, 2, 3, 4 tables that have the data we need in order to do these calculations and ensure that expired policy indicator is correct. So next up, we're going to jump in the DataForge. We're going to pull in these tables in a fresh project just to kind of show how to start from scratch and build it from the ground up to create this target column. And then we're going to go from there and show the kind of full end result and how that target column fits into the overall data warehouse and how easy it is to add more stuff over time. All right, here we are. We're in a brand new project. This is the DataForge UI for those who haven't worked with the platform before. We've got all kinds of different navigation over here. This is our kind of main screen, which is currently empty because there's nothing in the project. And what we're going to do is start by building some DataForge sources using the connections. So again, a connection is where a database is or where a source system is, files, folder location, server, and then the source is going to be essentially one source per table. So let's jump in and start building. As I mentioned previously, we have our tables that we're going to be grabbing from this lineage diagram. Again, each color represents a different table. We got 1, 2, 3, 4 different tables we need to grab from. So let's go through utilizing the connections feature to checkbox those and bring those into the platform. So if we go over to connections, I've already set up the connection correctly. I got the credentials in here as needed. But let's jump in and look at the specific tables that are available. In this case, it's in Postgres. For obvious security reasons, we're not going to be using the actual customer data in this example. So I took the exact same schemas, rough data types, everything like that was in Oracle, and I put them into Postgres. So let's take a look at the tables in here. Let's see if you want to filter, and let's just maybe filter based off of, because we've got a lot of tables in there right now. Let's go load AF group. So we got AF group. Here's our AF ref AF group association. That's what we need. So we're going to grab that one, and let's create a source there. Let's then grab, let's see, everything else is going to be, we got PC account, so PC, let's try to type in PC. Here we go. So let's see, we got account, we got PCX affinity group, I think was what it was. Nope, association participation, PCX this one. And we got policy period, and that's it. So where's policy period? Here we go. So we got our 3 tables here plus the one we added before. Let's initiate data pool on this one and get things kicked off. So now that we've gone through and created these sources, if I go back to that original screen, you can see we have 4 sources, each one of these representing the 4 tables we need to use in order to create this target column. 3 of them kicked off. They're going to begin querying the database, ingesting the data, and bring it into our data lake structures within the DataForge Managed Data Lake platform. Ultimately, that's run by Databricks under the hood. So as these things are processing, we don't need to sit and watch them. But once everything's in here, we can then begin working backwards from the target to the source and building up the logic to the actual final destination, which is going to be that expired policy. All right, now we've got all the data loaded. You see all these green checkboxes mean that the data was ingested correctly. It is now sitting in the DataForge Managed Data Lake within Databricks. So just quickly, reviewing, again, this is just test data. So we just have 100 records to keep things fast. You can see it went through each of the stages, ingestion, change data capture, enrichment, refresh, and of course we ran data profiling for it as well. We're not going to review what each one of these do in this, and just understand that once these processes are complete, there was no other setup required for these things to run other than what you saw as part of creating the sources and pulling the data. And now that these are complete, we have the information and the metadata to begin building logic and rules and calculations against the data set. So quickly just looking at raw schemas, you can see we have for this policy period table, we replicated everything. Again, because this is operating in Databricks, we converted it from Postgres types to Spark types so that we can begin operating it within Spark. That all happened automatically with DataForge. And again, there's a lot of details there about what happens as part of bringing data in with schema evolution, a lot of other features that we're not going to cover today. But let's take a look back at our diagram that we're going to leverage to begin building logic. And when you're working through this process, you're going to want to start from right to left and build up your logic one at a time with each one of these boxes. And that will then ultimately give you the correct results. Thankfully, with DataForge, we don't need to think about stages. We're just going to be thinking about individual rules or calculations at the column level. And so all of this here is no longer relevant. We don't need to worry about it. We can just skip ahead only to the blue boxes where transformations are going to happen. So the first couple rules we're going to tackle are these two conversions. These are currently in timestamp formats. Let's just go over here. Period start and period end. You see these are timestamps. This basically just puts them into a date format. If you want to look at this formula, into a date format for easier downstream processing with some date logic that they're going to use for those previous period calculations. All right, enough kind of preface. Let's jump in and build these two rules. So as mentioned, what we do is look at the we kind of look at the full pass-through. We got all these tables that live in between, but we know that in reality, this period start is just a normal column pass-through. There's no transformations done to it all the way from the source table. So in that case, we can go into our source here, which is this PC policy period, and we can begin building a rule. And we're going to build it one-to-one with these two. So we have this toDate, toChar, PC policy period start, so on and so forth. Let's now build the rule. Building a rule is very simple. We're going to give it the name, which is going to be policy effective date. You see it automatically gives us our target column name. And then in this expression box, we're going to be replicating that same expression. But we're going to do a little bit of aliasing along the way. So we got a toDate. Hit this little backtick. You can see all the Spark functions that are available to us. So we're going to toDate. See if toChar is there. Not there. We go. toChar. So it looks like there's a one-to-one function capability between Oracle, which is what this was written in, and Spark SQL. And so now we need to grab period start and then this rest of the piece. So let's grab period start. If I hit this open bracket, I get this. I can then do period start, which then references the same column that's referenced here. And then I'm going to be lazy and copy paste the rest of this because it should be the same logic if I can do it correctly. And there we go. And let's see, we got a bad thing. Let's see, what did I do incorrectly? Cannot resolve toChar period start due to data type mismatch. So it looks like the toChar function within Spark works differently than Oracle. I already knew this was going to happen. So actually all we need to do here is we don't need the toChar piece of this. We can just use toDate and this should work. There it goes. So again, as you're doing this conversion, there are going to be specific situations that you're going to need to adjust your logic to make sure that the data is correct as part of converting to a new version of SQL or a new different type of SQL with slightly different functions. Thankfully, in this example, it was pretty easy. And in fact, basically the toDate function within Spark SQL is a little bit more powerful than Oracle, and it's able to infer what you want to do with this syntax. But one thing you saw is that as part of development in DataForge, you're unable to save or you're unable to work through code that won't compile correctly. So again, as you're building, as you're working, you don't need to continue to rerun the data set or find the errors as part of executing the SQL against the data itself. As you're writing your expressions, you have real-time syntax checking. So let's save this rule. So that covers policy effective date. We're now going to look at basically the same rule here for policy expiry date. So let's build the same one. Is it policy expired or expiry? Expiry. Make sure I did that right. Okay. And then we're going to do the same thing. To date, open this dot period end, comma, and then it was just this part, get rid of a comma, and that should be correct. There we go. So now that we have these two rules, we have built this layer of the logic. So again, no stages needed, no full queries to say, hey, select from where, all these different things. All we had to do was write these two rules, and the result of these rules are going to be two new columns added to the table that has all of these raw columns on it, right? So what we did is we ingested the data, which created a table which has all 133 columns of the raw data, of course reconciled with change data capture to just be the current table. We can talk about slowly changing dimension of type 2 in a different video, but this is the current version. And then as we're writing rules, what we're doing are adding additional columns to that data set. And again, remembering column purity, we're not changing the number of rows. We're just basically doing scalar calculations to add additional fields to that table. So with it, we now have two new columns. I'm going to click recalculate, and it's going to kick off a process to begin building this new logic, running the calculation. And once it's done, we can jump back into Databricks. Let's see if I can do this live. And this should start very quickly. And it should give us results. Once this loads, you should see all 133 columns are two new columns that have the calculated logic for period start or policy expiry date and policy effective date. And if we scroll over here at the bottom all the way to the right, and you'll see policy effective date and policy expiry date. These are of date type, which again was inferred from the results of this calculation. We didn't have to set it. You can of course override it in these rules. But that's the process of building rules, is you're going to continually build, iterate, check your work by clicking recalculate, ensure that the data is accurate in your hopefully sample small data set. Maybe it's against the full data set. But then we're going to now take these two rules and continue to move from here left to build up the logic one rule at a time, leveraging data, which in this case just came from this policy period. But in the future rules, we're going to showcase how to combine data across multiple sources via relations. So let's look at that next. All right, we've come to the crux of the complexity of the logic. Again, everything so far has been pretty straightforward. We figured out what tables we need. We ingested the data set. We built some very simple rules to convert some timestamps to dates. Now let's get into some of the nitty gritty. So everything that's working here is primarily from the BV stage newer 15 bind account. And you can see there's a bunch of different formulas here. There's a bunch of window functions, this lag over, this kind of null value kind of coalesce that's going on here. Some more lags, some more window functions, so on and so forth. So, just to, kind of cut ahead and shorten this video a little bit, we've already done the analysis of this, looking at, this is the BV stage newer account in the original legacy system, the script that goes into it. Having it all in one place versus on that diagram actually is just a little bit easier to then see a common pattern. So if you look at this block of code here, which covers the majority of these calculations which were in our diagram, you start to see that there's a lot of code duplication, right? So they're using these window functions to calculate specific metrics by figuring out what was the previous policy for an account. And then once they figured that out via the window function and this lag function, you can see this lag is used almost in each one of these calculations. they then are doing a different calculation for each one of these, right? Sometimes they're just getting the actual number, right? So they're just saying, hey, this policy number is the previous one. Sometimes they're doing a complicated calculation, like calculating the term days, meaning how many days were in between the old policy and the new policy, so on and so forth. There's a number of different calculations they're doing. What you may notice, though, is there's a lot of duplication here. This could have been solved by first calculating, when or how, right? What was the previous policy, and then from there, doing a second set of calculations to do each one of these windows. And so that's what we're going to do in DataForge. Just to highlight, you could absolutely, again, in kind of the naive case, you could absolutely, just like we did with the two previous examples, you could totally just kind of more or less copy paste this data into rules, or this code into rules, pseudo one-to-one, just making sure that, the Oracle to Spark syntax is roughly equivalent. But we're going to do something a little different because we have DataForge at our disposal, and we don't ever have to worry about the cost of creating an extra stage. Creating an extra rule is basically free, whereas creating an extra stage, there's a lot of complexity. You need another storage layer, you need another script, you're adding another layer to the complexity. So with that, enough kind of preface, let's jump in and think about how we can refactor this code a little bit to reduce the amount of code in the logic and make it easier to understand for someone who may not be super familiar with why or how we're doing these calculations. Actually, before we jump into unwinding all that combined logic, we actually need to build our first relation. And a relation is used to connect two tables together. We need to connect two tables together because we have this account ID here. Account ID, tracing it back, comes from account. All the other fields that are used in this complex bit of logic are all coming from policy period, which we've already brought in. And we've also already brought in account. However, when we look at the way that policy period and account are connected in the original legacy code, we have a policy period, but then policy period is connected to policy, which is then connected to account. Meaning we have a table in between policy period and account in the source system data model. So we're going to have to bring in policy in order to make the jump or traverse through the data model and set up the relations and the combined transform model within DataForge to do these joins and make the connection correctly. So here we are back in DataForge. I've now brought in policy as that extra table we needed to connect policy period to account. And the next thing we're going to do is build relations to connect these different tables together. So let's jump in and do that. What we're going to do is build these join conditions. But again, these are called relations in DataForge because they have cardinality, a few bits of other metadata, and they're reusable across your rules. It's going to be policy period to policy. Give it a nice, easy name to remember. I'm going to go between policy period and policy. And then in my code here, you can see it's joined on this policy key here, this HKHPC policy. And in order to understand what this is, we need to trace the lineage of this. So I've already done this. Thankfully, it's nothing complicated. There's no calculations. It's a straight pass through on policy ID. So this is the same thing. It's just aliased in the processing chain many times, but it's ultimately just the policy ID. So thankfully, this data model is actually pretty simple. We have this.policy ID equals related.policy ID. And just explaining the syntax, anytime you see an open bracket, this is going to be a reference to a source or a table. And so in the case of this relation, you're going to say this. So that's referencing policy period. And then related is going to be referencing the PC policy here. And again, it's just a kind of lightweight syntax aliasing for us to work through. And this is going to work. And click save. And you now see our DataForge calculated that the cardinality of this relation, it's going to go from many on the policy period side to 1 on the policy side. And we have a nice graph view here. This is not super interesting, but you can see we kind of have the many and 1 view. So we've built our first relation between policy period and policy. Let's do the same thing now on policy. So we're going to jump over to that source, go to relations, and we're going to now, and you can see we have the same relation we built on policy. It's also, sorry, on policy period. You can see it's actually sitting here on policy as well. So you can see it from both directions, right? So in the context of policy, if we looked at this relation, it's looking at policy period, and the cardinality to policy period is many, right? Because we're now on the one side of the relation. So let's go policy to account. So policy, grab account, and I believe it is just account ID. Yep, equals related dot account ID. Again, doing the same process, looking at the join condition in the legacy system, tracing the lineage back to the source system, to the original IDs. And this was thankfully, both of these were simple joins between the two. Click save. Now that we look at the graph, we have our nice connection here, right? So now that we've set up our data model, we've said, hey, from policy period, we can go to policy, from policy to account. We now are able to begin using account information or account fields, and policy fields if we want to, but account fields at the policy period level. And that is because this is a many-to-one and many-to-one. Anytime you're traversing through a many-to-one relation, you're able to freely use the columns that are available up the chain without creating data duplication while staying in the column pure world, which is very important, and again is part of the core framework of how you develop logic within DataForge. So with that, we now have all the pieces we need to rebuild that complex previous period window functions and the logic associated with it. Okay, let's jump in and rebuild the logic of all of these different lag functions. What we're going to do is first figure out what the previous policy ID is, and then from there we'll be able to save that as a function, save that as a rule, and then by leveraging that with downstream in the many other rules, we'll be able to basically eliminate a lot of this code duplication. And again, funny enough, they actually have the function that we want to build to then leverage downstream in the many other rules and get rid of all this code duplication already built for us pretty much. And it's this previously policy period ID function. So again, we're not reinventing the wheel here. We're just using the DataForge framework to eliminate code duplication. So let's copy paste this in and edit it with the DataForge code. So it's going to be previous policy period ID. Copy in our code. It's going to yell at us and say these things don't exist. But now this is going to be from this. And then account ID is obviously coming from account. And policy effective date is from this. Anytime you have a window function, you need to mark it as keep current. All the difference between snapshot and keep current means is keep current is going to make sure that the entire table will be taken into effect whenever the calculation is done. Snapshot is just going to be for the batch in question, right? So if you're doing incremental loads, this is something important that you need to think about, but it's kind of outside the scope of us rebuilding this now. For the most part, the system will tell you when you need to do snapshot or keep current, such as in this example, it told us, hey, you can't save this rule unless it's marked as keep current. So we got it set up in keep current. You can also see that we did reference account ID through those two traversals. We went from policy period to policy to account. And here you can see that relation path, right? So it's saying, hey, you referenced something from account. There's only one path currently set up in the data model on how to get there. So it doesn't give us any options to select to the joins, but that obviously would be possible if there were multiple paths. And here's the path, right? We're going to go from policy period. We're going to use this relation to get to policy. Then from policy, we're going to use this relation to get to account. Very straightforward. Click save. Yes, there are nulls because I'm using mock data. If this was actually kind of primary key, foreign keys in the database, it wouldn't give us that error. But again, good warnings and things to help you try to prevent you from making mistakes. So once we have this previously policy ID, we're going to do something pretty unique. And we're going to build what we call a self relation. It's almost like a self join. to then allow us to build all those derivative functions or rules or columns that are from the legacy code based off of that self relation. Now that we have the previous policy ID calculated for every policy that has a previous policy, let's now do a self join between this existing hub table and itself to then join between the current policy and the previous policy columns, such that when we do that join and we traverse that join, we'll then be referencing all the data associated with that previous policy. So let's jump into relations. We're going to do policy to previous policy. Sorry, policy period to previous policy period. Our related source is actually going to be ourself, PC policy period. We're going to do this dot previous policy period ID, which is our calculated rule, is equal to related dot policy period ID. And this is actually going to be a many-to-one relation because we're going to be moving from what could be unique on one side to what is definitely unique on the other side, right? Each line item within the policy period will have exactly one record in the existing table that will have it. There may be other ones in a weird data modeling scenario where there could be a branching thing in terms of previous policies, but in this case we know for sure that it's only going to be referencing one line item on the previous policy. And because again it's a many-to-one through this self relation, we can now reference it in rules and get rid of a lot of that code duplication from the legacy code base. Now that we got our window function set up and our self relation set up, and as I was recording this, I realized we actually missed one date calculation. So again, a lot of these things were timestamps. We need them to be dates in order to do some of the functions downstream. And the one I missed was cancellation date. So it was in this this wonderful mess of code, which again we found out as I was working through the next section of the video. We have policy cancel date. Policy cancel date, if you look at it, it's essentially just a date conversion on cancellation date. So let's build that right now. So policy cancel date, very simple. We're actually just do this dot cancel date, and then we could wrap it in a cast function, but we can use this nice drop down, and then it'll save it as a date type, and that makes it very straightforward. Now that we have expiry date, effective date, and cancel date, we can work through the next piece of this, which will allow us to do some more calculations. Okay, we're finally there. Let's look at one of the more complex calculations. Again, what we're doing is breaking this down into smaller rules to promote code reuse and get rid of the copy paste of this same logic everywhere. So what we've done so far is actually get rid of this whole lag over partition by, order by, policy effective date. You can see, this chunk of code right here is replicated many times, and then actually everywhere you can see this chunk of code is copy pasted a whole bunch of times in every rule, multiple times sometimes even. So the first part is we got rid of all this that was consolidated into that single rule and that self relation. But let's look at an example that we're going to then leverage that rule and reference it. So we have previous term days that has this crazy lag function and a bunch of other stuff. If you get rid of all the noise around the lag function, it's just saying, grab the cancel date if it exists. If not, grab the expiry date and subtract that from the effective date. Basically a date diff between the combination of cancel date and expiry date. And that will allow us to get the right stuff. And then if you actually look around a little bit, you'll see they have this thing called policy end date. Policy end date is the combination of cancel date and expiry date. You can see that's used a whole bunch of times over and over again. So the first thing is let's create something called policy end date that will then get rid of having this copy pasted null value of these two things together. Put that into a rule. We'll then reference that, and then from there we'll keep building up our logic. So let's do that really quickly. We'll go policy end date. Go this dot cancel, policy cancel date. I think it's just NVL, same syntax. And I believe it was expiry date. Let me just double check I got that order correct. Yes, cancel date, expiry date, policy end date, save. Okay, so now we have this. Now we can replace that snippet of code every time we see it. And then looking at the function here, which is previous term days, this is again policy end date minus the policy effective date, but in the context of the previous policy. And again, getting to some advanced concepts here, but let's just say, whether it's in the context of the previous policy or this policy, let's just create, the term length, right? Whether it's the previous policy or otherwise, let's create the rule to calculate the term in days. So let's just call it term days. And we're going to do this dot policy end date minus this dot effective date. Now we have previous term days. Policy end date. There we go. What did I do wrong? That should be a date. I think maybe this was coming back as a date. It should be. Oh, yeah, okay. You can't just subtract the dates with Spark. There you go, right? So this is another example of how Oracle and Spark operate a little bit differently. So term days, we need to use a date diff function. That subtraction on the days, it's not going to return the integer we want. So we're going to have to do date diff. And that's going to be this dot policy end date minus, comma, this dot policy effective date. There we go. And we're going to get an int response. Great. We now have term days. And with term days, we can now calculate, finally, previous term days. And so the way we are able to reference previous term days is by referencing that self-relation. It's very simple syntax now for this rule. We're going to reference this here, and we're going to do term days here. And it's saying, hey, look, you're referencing PC policy period, and you're doing that via this self-relation, which takes into account the lag function and the join to itself to reference the previous policy period. So as you can see, we took what was a nasty bit of work, this whole section of code here. We broke it down into component parts, each kind of sub-function buried within this complex function, and we converted them into reusable elements that can then be referenced by other functions, by other calculations, right? So now that we have all of these different functions built, we can look at each one of these other line items, such as policy period ID, previously policy period ID, and they all become relatively trivial to create now that we are no longer copying and pasting code everywhere. So actually, as I was finishing building out this layer of logic and moving over to new renewal indicator, I found out that one of the previously gray boxes actually should have been blue. This baseline new renewal indicator had a case statement built into it and actually had a whole new stage that they put together. And this really highlights the difference between developing in a scripting pipeline or really any other tool besides DataForge. It's up to developers to figure out when to build new stages for code reuse and to work through how to group their code together for the most efficient processing, balanced with the least amount of copy paste. So we saw a lot of that example here with all of this copy paste here. So this is kind of the bad version of it, right? This is definitely not fitting into the don't repeat yourself or dry principles. This is a lot of repeating yourself. However, they tried to combat that by building a whole new stage here, this new renewal 25 baseline. If we go over to there, you'll see that by breaking this out into a separate stage, There's no lag logic in here. This is a pretty straightforward, simple case statement that was made possible by creating a separate stage. Whereas in DataForge, you no longer need to think about the stages. You don't need to think about that. You just can build each rule one at a time. Each rule is almost like its own separate stage, standalone. You can reference it just like it was its own separate SQL statement or own separate stage within your processing pipeline, which then ensures that you're never going to repeat yourself. You can always break down the logic into its most component parts and then reuse those component parts many times over. So this is one of the key ways we help eliminate code duplication. I already built out this rule within DataForge. Again, just taking the same references here that it was going upstream. And then the last thing I want to mention before I show the kind of final solution here and the lineage of it and how you can then understand what's been built as you worked kind of forward. We worked kind of backwards to forwards, forwards to backwards. You can see here, right, rules like this where they end up being very simple, right? We have this previous total cost report here. They were built in the stage, for what made sense at the time. But if you look, there isn't really a benefit to this rule, right? The syntax of, referencing it this way or the syntax of referencing it with this, there's really this rule doesn't do anything, right? So it's, what we're going to do eventually is eliminate rules that look like this, that are just kind of passed through logically. And we're going to reference things like this directly in the downstream rules once we work through everything. So fast forward, we have built out the remainder of the logic to do expired premium. One thing important to note in order to get to this final target column is we had to bring in additional tables and we had to join them via relations in order for all the references that were in the new bits of logic here, this new renewal indicator and expired premium, we had to bring in a couple more tables. So again, here's our diagram. Previously, we had brought in the tables for policy period and account, as well as a table hidden in between these two called policy to connect between policy period and account. We had two more we knew we needed to get data from, which is this AF group or affiliate group, as well as association participation here. Let's take a look at the data model we had to build in order to bring those reference tables in as well. One nice thing is within DataForge Cloud, we have a visual way to look at the data model that's sitting behind these rules. And again, typically this data model wouldn't be in one place. The joins would be buried in the scripts, right? So again, just kind of going back to this type of example, BV stage load, right? Basically all of these joins, they actually would be here in these join statements buried within a specific script somewhere. They're not in a central location that's shared by the entire platform. And as you can imagine, the joins that are used here oftentimes are replicated many times over within the multiple layers of the different stages. For example, here we have joins. Actually, some of them are the exact same joins between them. For example, between policy and policy number here, they're replicated, so very very duplicative in their code. Whereas in DataForge, it's all in one place, and these then are referenceable across many different rules and relations, so on and so forth. We have 6 sources or 6 tables required in order to get all of the logic built for expired premium. Again, let's look at expired premium, and for example, we talked about the kind of term days and looking at this syntax of this dot previous term days versus this. And it becomes clear that these two rules, after we've built out the logic and kind of understand it a bit more in the final state, these two are not needed anymore for rules or calculations. And in the spirit of being clean and having as little code as possible, let's delete these. So within DataForge, you can go in and delete rules, and it's perfectly happy to delete these 2 rules because they're not being used anywhere in downstream logic. However, if you look at something like coverage lapse days, and you see these highlightable links, these mean that they're pointing to a function upstream. Everything that's not highlightable, these are going to be raw attributes that are happening elsewhere. So for example, though, if we try to delete coverage lapse days, because we think, hey, we don't need this, I don't need this anymore, the system won't let you. It is always checking every bit of logic in the entire platform across every source, not just this one source, not just this set of rules, but every single function or every single rule in the entire platform, every single target in the entire platform, to ensure that when you're trying to delete something, it'll prevent you from doing so if there's a downstream bit of logic dependent on it, which can give you confidence to clean things up, if you think that's possible, and then work through any potential dependencies otherwise. The last thing I'll kind of talk through is Lineage. So what's really great is, this is a nice way to view the data, or sorry, the transformation code. You can see it's very clean. We're just down to 10 rules versus the thousands of lines we had before that were built in order to support this pipeline. This is the exact same logic that is all here is now simplified into these 10 rules, which again is very, very powerful in and of itself. But what's also great is, now that we have things in DataForge, we do have column level lineage, which whereas before we had to build that whole diagram out by hand because again, there wasn't an observability tool that could do it for us after the fact, and the scripts were messy. Here, because we built things in DataForge, really straightforward to understand, all the different dependencies between the different sub pieces of logic. And at any point from this diagram, you can jump in and see exactly what that box of logic does, what the expression is, and then how to trace back exactly what's happening for that specific column calculation. Now that we have everything built in our rules, we're going to look through where to put it, right? So I think going back to the very beginning of part one of this, the target system for this is actually Snowflake. So everything here has been happening in DataForge and underneath the hood Databricks. However, they want their target data warehouse to be in Snowflake. So let's look through how we can then take all this logic, take these columns, and publish them to an external system. So far, we've covered building sources, and as we hope, you would be doing most of your logic in sources. A reminder that sources are the column pure, functional, declarative side of DataForge. Becomes very straightforward to add more logic to these objects if you're able to fit them within the column pure framework. However, this is not the only place where you can build things. This is column pure, where you need to do row pure calculations, you want to publish to an external system. You do that via outputs. So let's look at building an output. Similar to sources, you give it a name. So this is fact OMR. Again, we're going back to the we're going back to the code, right? The legacy code, just so we get it right. Fact OMR bound. This is the table definition of the fact table that we're looking to eventually replicate. And what we're going to do in this example is just publish a few of these columns, and we'll talk about why and how to add more over time. So here we go. Fact OMR bound. Data warehouse, fact table for policy period. Let's do table name is going to be this fact OMR bound. Let's just give it 2 because we already have one. This is a second example in our target table. Schema is going to be this. Let's look over here. We have EDWIM. And again, here we kind of already have the dimensional model built out as a previous example. But let's put an _2 here. And we're going to put it in the EDWIM. Again, we're now in Snowflake. So we've jumped technologies again from DataForge and Databricks over to Snowflake. And so again, let's put it in the EDWIM, EDWIM schema. And let's grab the connection, which points to the demo database. So we're in demo, EDWIM, and we're going to create a new table, fact OMR bound 2. Again, this table doesn't exist yet in Snowflake. It would be a new table that DataForge is going to create and manage for you. Once we click save, we're popped over to the mapping table. The mapping table does 2 things. It defines the target columns and target schema of the destination table, as well as where the data is coming from within the DataForge Lakehouse or the DataForge Hub. So the first thing we're going to do is add some columns. What does the target table look like? And then from there, we're going to do the mappings. So let's add some basic ones. Going off of our definition here, we have account ID for one of them. We of course want to do our expired premium. We put so much work into building that. We also, know, hey, look, as part of computing expired premium, we needed to create this new renewal indicator. So let's add that. That's a great column that we already know is built correctly. And then let's add some more IDs just to, make it easy to slice and dice this data by some dimensional attributes. Your policy period ID. Here we go. And then maybe, let's see, AF name. That was a good one. The affiliate group name. We know we have that as well. And so now we've defined target column names. These don't have data types yet because we haven't defined them. We could define them manually, but in this case, we're going to let DataForge do some stuff for us. The next step after we've defined target column names, and this can be done in any order, but this order is the easiest to work through, is we're going to be adding where the data is coming from. So if you remember, all of our logic was built here at this PC policy period. This is the grain of data that we know we want to publish because the metrics are calculated at that granularity, which is very common in a fact example. You want the fact table to be kind of the transactional level of data. So let's grab that policy period, click save, and you can see it did a lot of stuff automatically for us. So we use some basic fuzzy matching in order to automatically map columns that have the same column name, and it also inferred data types. So we have in the back end mappings between the data types within Spark and Snowflake to do this. We do the same thing on ingestion, so from the source system into Spark, and then from Spark to the target system, we pick the smallest possible data type and say, look, this is probably what you want. But of course, you can change this if you want, right? So, hey, we can do number, double text based off of the things that have been mapped. All three of these are possible data types for that target column. We're going to leave it as number, and we're going to leave it exactly, what the inferred things are for simplicity. The only things that were automatically mapped, though, were things that were connected directly or columns that were directly available on policy period. And those can be either raw attributes or rules. The things that are not getting automatically mapped are references to other columns that are in other sources that are not on policy period. However, within output, the only transformation, the only type of thing you can do in the mapping is a reference across a traversal. You can do no calculations or no SQL expressions, or you can't write rules here, but you can do mappings. And this, again, it prevents writing trivial rules. So we're going to grab account ID from account, kind of same thing. Here's the traversal used in order to go get that reference data. Same thing with AF name here. There we go. And we now have all the data mapped, all the target column types defined. And the next thing we're going to do is kick off a process to create this table, populate this table, and begin working with it and managing it like a production workflow. Now we have everything defined. Let's kick off a process. So I'm going to click Reset Channel Output. One of the nice things is we don't need to hook up an entire orchestration or workflow. We can kick off this process just from the output stage, as we call it, to take the data that's already sitting in the lakehouse and generate a new process to publish this data. You can see here, again, it generated this process. It's going to run a pretty simple query against the data set living in the lakehouse, take the results of that query, and then publish it to Snowflake, doing the proper data type conversions and etc. So again, pretty quick. A few other things that happened under the hood. Again, easy kind of logging here to see what's going on. It went through and created a new table, added some new columns, right? So here's a create table statement, ran some DDL in order for the table to show up correctly here, OMR bound 2 in Snowflake. So again, DataForge is able to control, manage, and operate on top of Snowflake at the output layer, so that if a business wants to engage with the target data set in Snowflake, SQL Server, we support many different outputs. You can use our output feature to do that, and of course this data works just as good as data sitting anywhere else, and has everything hooked up properly. You can see we do have a few system columns here. These help with the change data tracking and the operational efficiency all the way from ingestion through to output. With everything hooked up from source to output, we can now look at the end-to-end data flow for this policy period. So I can kick off a new ingestion. It'll bring in a new batch of data. that so long as the settings are correct and our incremental load parameters are correctly defined, the platform will now basically bring the data all the way through the chain, through all the references, join all the data sets, set up all the orchestration correctly, and then publish the data to the output. So whereas previously it would have finished with refresh because there are no outputs hooked up to this chain of logic, now that we have the output defined, it will then add on an output step, which you'll see jump in here shortly, to take this data and publish it to the target. And so again, what's been really hopefully clear is that at no point in this entire development process have we done any orchestration. We've never told the system, hey, first run this source, then that source, then this stage, then that stage, then this bit of logic, and then finally push the data right to our target table. That procedural way of thinking is no longer relevant if you're working within the DataForge framework. You can just think about things column by column, rule by rule, build up your logic, and all of the actual orchestration, the stage design, the coordination between all the different elements in the platform are handled for you, and it's all done implicitly through the way you've defined your rules. So now that we've and your mappings and your outputs. So now with this final solution, again, we have a production ready pipeline that we could again promote, which again we can cover in another video through our DevOps process, or maybe just run it live here day to day if it's something less important. And again, we have this target table here, and again it'll be refreshed as needed. We also have again really granular lineage tracking at this layer as well, right? So again, just to highlight, now that we have this now target mapping here, right? You can see, hey, look, we affect OMR bound, which goes through this mapping, which then goes through this whole piece here, right? So from all the way from the source to target, the original tables in the original system, all the way through the target data warehouse, we have clear lineage at the column level, which is a very powerful way to understand and govern your data platform. We've covered a lot in this example. As I mentioned before, this was a small subset of the overall project, but a relatively complex one. And we highlighted a number of things. We highlighted how building in DataForge can compress stages. You saw in our diagram, 20, 30 stages were developed for various reasons. Some of it for code duplication, some of it for logic for the different stages around slowly changing dimension type 2. We didn't cover that in our example here today, but DataForge also automatically builds slowly changing type 2 dimensions under the hood. That would have had to be manually defined in those scripts, in those stages. But we also covered how to think about building rules, how to build relations, how to build this consolidated data model, and also how to iteratively build and add more columns to the data model over time. An important thing to note is, as part of this process, we built 4 target columns in our output. What's really important to note from a kind of a high level is once those columns are built and defined, they are static in that adding more stuff to this platform, adding more logic to DataForge will not interrupt or will not change the logic associated with those 4 columns. So those 4 columns could be sent over to QA, or they could be refined and defined or fixed through the kind of quality assurance process or the business engagement, looking at the reports, making sure the numbers are right, or reconciling versus the legacy system. And once those columns are validated, what's really powerful with DataForge is they no longer need to be revalidated or re-looked at every single time another column is added to that table. Because all the logic is defined in a columnar fashion, because all the rules are defined in a columnar fashion, unless a column calculation is changed that's part of the chain to populate those target rules, we no longer need to worry about, we'll call it cross-bleeding between columns. And that is again because the actual logic itself is delineated by column, whereas in a traditional stage-based or script-based or node-based or model-based set of rules or logic, everything is done at the table level. And anytime things are done at the table level, you have the risk of, by adding logic to that model, that DBT model, or that coalesce node, or that script, to potentially affect or change other columns or other things in that script. And DataForge, we prevent you from doing that. It's impossible. The system does not allow you, and you saw some of that when I tried to delete some of the logic. It does not allow you to make changes to things accidentally or not on purpose. so that you can then completely change how your project is run, and have a much more iterative, incremental building, loading, quality assuring, publishing, production ready set of operations, to dramatically speed up the cycles of the team. No longer you can have these kind of waterfall approaches, or big hit, big build, publish everything and then try to get everything right. And then every time you fix something, you break something else. We've all been there. DataForge kind of, again, revolutionizes how developers work. And we do it through breaking down the logic to this columnar level, which is unique to us and is one of the most powerful ways to reduce the amount of code duplication, as well as reduce the amount of regression testing needed when building out these solutions. Hopefully this was super helpful. We really are looking forward to more engagement, and we have a lot more to cover within DataForge to look at different patterns, different approaches to these types of transformations. Please like and subscribe, and give us, share us on the social media platforms, and also please reach out to us. We love, to hear your comments, and really hear and see what you guys think about what we have. Thanks so much, and see you again soon.